In this video, we're going to talk about proving figures are congruent by using rigid motions. So first, we need to make sure that we understand the meaning of congruent. Two figures are congruent if they are exactly the same size and shape. So that means that all of the corresponding sides are equal to each other and all of the corresponding angles are equal to each other. So if two figures are congruent to each other, then we can prove that by using rigid motions to map one figure onto the other. Remember, when you map one figure onto the other, that means they match up perfectly. And the reason why that works is because rigid motions are motions that do not change the size or shape of the figure. So in this example here, I want to see if I could prove that these two quadrilaterals are congruent to each other by using a rigid motion to see if I could map quadrilateral JKLM onto quadrilateral CDEF. So I want to see if I could do that by either translating, rotating, or reflecting one quadrilateral onto the other, because those are the rigid motions. So if I look here, this looks like a symmetrical pattern. Symmetrical patterns come from reflections. So this looks like this could very well be a reflection across the y-axis. So remember that when we reflect a figure across the y-axis, what happens to the ordered pairs of each point is that x comma y becomes the opposite of x comma y. So in the quadrilateral CDEF, point C is at -6 comma 7. That would put point C prime at the opposite of -6, right, is 6 comma 7. D is at -8 comma 2. That would put D prime at +8 comma 2. E is at -2 comma 4. That would put E prime at 2 comma 4. And F is at -4 comma 8. That would put F prime at 4 comma 8. So if we plot the points, we see C prime is at 6 comma 7. Notice this graph is counting by twos. So 2, 4, 6, and then 2, 4, 6, and then halfway between 6 and 8 is 7. So this is the location of C prime, which we see is the same as J. D prime is at 8 comma 2, so 8 comma 2, that's right here. And that's the same location as K. E prime is at 2 comma 4, 2, and then 2, 4, and that's the same location as L. And F prime is at 4 comma 8, which is right here, and it's the same location as point M. And so we see that if we reflect quadrilateral CDEF across the y-axis, it maps perfectly with quadrilateral JKLM. So we have just used the rigid motion of reflection to prove that these two quadrilaterals are congruent to each other. And so the way I would write that is quadrilateral CDEF is congruent to quadrilateral JKLM. Now it's important to write the names of these figures in the correct order. So CDEF is congruent to JKLM because point C corresponds to point J, and point D corresponds to point K, and point E corresponds to point L, and point F corresponds to point M. And we could also do this with the sides. So we see here CD corresponds to JK. That means that this side here, CD, corresponds to and is congruent with this side here, JK. So let's take a look here and see if we can figure out whether or not triangle ABC is congruent to triangle XYZ. So which rigid motion can we use here? If we were to translate it, then both triangles would be in the same position, just in different locations. If we were to reflect it, they would look opposite of each other, and they don't really look opposite of each other. So this might be a rotation. So it looks like it could be a rotation counterclockwise 90 degrees. So we can go ahead and test out whether or not that is true. So remember, when you rotate counterclockwise 90 degrees, the pattern of change for the ordered pairs is x comma y becomes the opposite of y, comma x. So if you look at the ordered pairs for triangle ABC, we have to recognize that this graph is counting by twos. So point A is at 8, comma, negative 2. Point B is at 8, comma, 4. And point C is at 4, comma, negative 2. If we apply this pattern, we see that A prime should end up at, so opposite of y, comma, x, so 2, comma, 8. B prime should end up at negative 4, comma, 8. And C prime should end up at 2, comma, 4, because we're taking the opposite of y, comma, x. So let's take a look at where these points end up. A prime would be at 2, comma, 8. So that's right here, exactly where x is. B prime would be at negative 4, comma, 8. So here's negative 4, 2, 4, 6, 8. That's exactly where y is. And C prime would be at 2, comma, 4, 2, comma, 2, 4. Exactly where z is. So we see that triangle ABC maps perfectly on triangle XYZ. So then we can write triangle ABC is congruent to triangle XYZ. And so that means that angle A corresponds with angle X. That means they're equal to each other. And angle B corresponds to angle Y. And angle C corresponds to angle Z. And that also means, for example, that side BC, which is here, corresponds to side YZ, which is here, and that also means that they are the same length. So in this example, they're telling us that triangle ABC is congruent to triangle PQR. What we need to do is figure out what sequence of rigid transformations took place in order to map one triangle onto the other. Remember that this statement here is not only telling us that triangle ABC is congruent to triangle PQR, but it's also telling us that point A, or angle A, corresponds with point P, or angle P. And B corresponds with Q, and C corresponds with R. So now we have to be kind of like a detective. We have to figure out what sequence of transformations would take point A from here and bring it all around here where point P is. They correspond. So if I think maybe about a rotation, I see that point A is 1 off from the negative 8, and I know that a 90-degree rotation clockwise would put it here, 1 off of the 8 for Y, and another 90-degree clockwise rotation would put it here, 1 off of the 8 for X. Well, it's just pretty close to where P is. So maybe a rotation, and then just to slide it over, right? So maybe a rotation and then a translation. So let's go ahead and test it out and see if that works. So we know that the pattern for a 180-degree rotation for the ordered pairs of the points is that X, comma, Y becomes the opposite of X, comma, the opposite of Y. So here we have A is at negative 8, comma, negative 2. B, notice B is halfway. This is counting by 2. So this is negative 2, negative 3, comma, negative 6. And C is at negative 2, comma, negative 2. So then that would put A prime at 8, comma, 2. And B prime at 3, comma, 6. And C prime at 2, comma, 2. So we see that A prime ends up at 8, comma, 2. That's right here. B prime ends up at 3, comma, 6. So 2, 3, comma, 6. That's right here. And C prime ends up at 2, comma, 2. That's right here. And you see this triangle is very close to triangle PQR. All we have to do is translate it to the right. So how far do we need to translate it? Well, if you look at the difference between the x values of a prime and p, the x value for a prime is 8 and the x value for p is 9. So we really just need to move one step to the right or add 1 to the x value. So what we have here is a translation where x comma y becomes x plus 1 comma y, because all we're really doing is moving everything one step to the right. So if a prime is at 8 comma 2, then a prime, or in this case p, is at 9 comma 2. And if b is at 3 comma 6, then b prime prime or q is at 4 comma 6. And c prime prime or r is at 3 comma 2. And if we plot these points, we see that p is indeed at 9 comma 2 and q is indeed at 4 comma 6 and r is indeed at 3 comma 2. And the rigid motions that were used were a 180-degree rotation followed by a translation of x plus 1, because we just moved one step to the right. So in this next example, we see that quadrilateral ABCD is congruent to JKLM, and we need to figure out what series of transformations were used to map one onto the other. So if I'm looking here at JKLM, and I look at point M, which corresponds to point D, they kind of look opposite of each other, right? And if I think maybe if I were to be able to take this and move it up here, then it looks like they might be symmetrical. This could be a reflection, but obviously a reflection wouldn't be enough. It would also have to be, maybe after reflecting it, a translation. We'd have to move it downwards. So let's go ahead and see if that's the case. So again, in a reflection across the y-axis, the way the ordered pairs change is we take the opposite of x. That's what happens when you reflect a figure across the y-axis. So in our little table here, we see that point A is at 2, 3, comma 4. So that means point A prime would be, we take the opposite of x, so that would be at negative 3, comma 4. Point B is at 2, 3, comma 8. So B prime would be at negative 3, comma 8. C is at 4, comma 9. So C prime would be at negative 4, comma 9. And D is at 8, comma 8. So D prime would be at negative 8, comma 8. So let's go ahead and plot these points and see where that puts us. So A prime would be at negative 3, comma 4. That's right here. B prime, negative 3, comma 8. That's right here. C prime at negative 4, comma 9, which would be here. And D prime at negative 8, comma 8, which would be here. And so we connect the dots. So you see there, that looks like a proper reflection of the figure across the y-axis. So now we need to figure out how we need to translate this figure so that it maps on top of JKLM. So what we can do is we can pick a point and its corresponding partner and see how the x and the y values change. So let's do that with A prime and J. So we have here A prime, we already know is at negative 3, comma 4. And J, let me put J in red, is at where? J is at negative 1, comma negative 6. So now, what is the relationship between negative 3 and negative 1? And remember, it has to be one of addition or subtraction. So in order to turn negative 3 into negative 1, I have to add 2. So we're saying x comma y becomes x plus 2. And now let's take a look at the y values. What do I need to add to positive 4 so that I end up with a negative 6? And that would be a negative 10. So y minus 10. So this is the translation that is taking place here. So now we can go ahead and do the same thing for the rest of the points. And so we have b prime is at negative 3 comma 8. C prime is at negative 4 comma 9. And d prime is at negative 8 comma 8. So then b prime corresponds to k. And so how are we going to get to k? So what is negative 3 plus 2? That is negative 1. And then what is 8 minus 10? That is negative 2. And then c prime corresponds to L. So negative 4 plus 2, that's going to be negative 2. And 9 minus 10, that's going to be negative 1. And d prime corresponds to M. So negative 8 plus 2, that's negative 6. And 8 minus 10, that is negative 2. So let's plot these points and see if we got it right. So J is at negative 1, comma, negative 6. That's right here. K should be at negative 1, comma, negative 2. So negative 1, comma, negative 2. That's right there. L should be at negative 2, comma, negative 1. So here's negative 2, comma, negative 1. And M at negative 6, comma, negative 2. So that's negative 6, negative 2. And we see that after the translation, we map perfectly onto JKLM. So our series of rigid motions was a reflection across the y-axis, followed by a translation of x plus 2, comma, y minus 10. Last part of this lesson, we see that we can do the same thing with line segments and angles. So I'm looking here at these 4 line segments, and I'm trying to figure out which one of these line segments is congruent to the other. So I could kind of count a little bit on the grids to see if I see any of these that are the same length. So if I take a look at GH, right, to get from G to H, I have to go down 2 and right 1, 2, 3, 4, 5. And to get from E to F, I have to go up 2, 1, 2, and to the right 1, 2, 3, 4, 5. So these 2 line segments look like they are the correct length. So then what rigid motions could I use to try to make sure that they are congruent? So for one, I can reflect GH across this line here. So that would put G as 1, 2, 3, 4, 5 to the left. So I go 1, 2, 3, 4, 5. So that would put G prime here. And this would give me this line segment from H to G. Then all I have to do is figure out, well, if I translate HG prime down, will it map over EF? So if I take a look, to get from H to E, I would have to go left 2 and then down 1, 2, 3, 4, 5. So in other words, I would have to do X comma Y becomes left 2, that's minus 2, and down 5 for Y would be minus 5. So now if I do that and I move H to the left 2, 1, 2, and down 5, 1, 2, 3, 4, 5, that maps H right onto E. And if I do the same thing with G prime, left 2, 1, 2, and down 5, 1, 2, 3, 4, 5, that maps G right onto F. So we can see here that these 2 line segments are congruent. So line segment GH is congruent to line segment EF. All right, so now let's take a look at these angles and see which ones are congruent with each other. So if I look at B and C, okay, and I think about maybe B and C, what if I were to take C and reflect it and then translate it? So what I'm going to do is I'm just going to put some points here. So I'm going to put a point here, and I'm going to put a point here. So I'll call this, D, and I'll call this E, just so I can give them a name. And what I want to do is I want to reflect across this line here. So then here's C is 2 to the right of this line. So C prime would be 2 to the left here. D is going to stay right there in D prime. And E, right, is half a step to the right. So now E prime here is going to be half a step to the left. So this is my angle. That was bad. Let me do that again. This is my angle here. All right, so now let's see if we could map this angle onto this angle. Now, to get from C prime to B, I would have to move left 1, 2, 3 and a half, and then 1, 2 and a half up. So left 3 and a half and up 2 and a half, and that would put me right here where B is. So let's do the same thing with D prime. So I'm going to go 1, 2, 3 and a half, and then left, and then 1, 2 and a half up, and that puts me right here. So we'll call this D prime prime, I guess. C prime prime. And over here, we have E. So we're going to move half, 1, 2, 3, and then 1, 2 and a half. And that puts E prime prime right here. And so when we connect them together, we see that the angle does map onto the other angle. Now remember, you're saying, well, C prime prime to E prime prime is shorter than B to this end of this arrow here. Remember, these are rays. Rays go on forever. So what matters here in terms of whether or not the angles are congruent is the degree of opening here. And so you see that both of these, they map perfectly on top of each other, and they have the same degree of opening. All right, so now you should understand the concept of proving that figures are congruent by using rigid motions.